Hello again, everybody. In this video, we're looking at the chi-square test, and we're going to do two problems. One that looks at the chi-square goodness of fit test, and the second that looks at the chi-square test of independence. Chi-square is a non-parametric test, which means you can look at data that is not normally distributed. In this case, we can look at categorical variables like ordinal or nominal data, and we can look at whether the proportions are, basically what we're analyzing are questions about the relative proportions or frequencies of various categories. So there's much more detail, but I want to save the introduction, or I want to keep the introduction relatively short because I want to focus on the actual computations involved and interpret values as we go. So here it says a researcher is interested in knowing if there are more female doctors under age 30 compared to male doctors under age 30. If the researcher collects the following data, what will be the conclusion using the chi-square test for goodness of fit? All right, in other words, the researcher goes out and samples a group of individuals. In this case, we have 320 people in our study. And how did I get that? Because essentially 143 plus 177 told me that the total is a sample of 320 people. Okay, so what we're essentially going to ask is, are there more female doctors under age 30 compared to male doctors under age 30? Now, if there were no significant differences in the proportion of doctors that were males versus females, you'd have a 50-50 split. 50% of your sample, or excuse me, 50% of your population would be male and 50% of your population would be female. So essentially what we're asking is this sample data significantly different from a 50-50 split? So the null hypothesis is saying that there is no difference between groups, that they have what I'll put as equal frequencies or equal proportions between groups, between samples. And the alternative hypothesis, on the other hand, is saying, no, they're not equal. We have some unequal frequencies. So frequencies are not equal. Between your samples. All right, so something to that effect. And we are given this information, well, I should say a researcher went out and asked 320 doctors under age 30 whether or not they are male or female, and 143 said male, 177 said female. These are the observed frequencies. I'm going to label that FO. This is the frequency or the data that the researcher actually observed. And the way chi-squared tests work is you compare your observed frequencies to the expected frequencies if the null hypothesis were true. So what I'm getting at here is we need a new table called the expected frequencies, FE. And I'm going to create this table right now. So we have the males, the females. Now these are the expected frequencies if the null hypothesis were true, which says equal frequencies between samples. So that means that if I had 320 people in my sample and that there are no differences between how many males and females there are, you would expect 160 in each group. That would be if these proportions are equal. Now, obviously, our proportions are not equal. 143 is not the same number as 177. But is that difference just due to sampling error, or is that a statistically significant difference between these two groups? That's what we're trying to find out with chi-squared. And so take a look at the formula for chi-squared. Essentially, in the numerator, you're comparing your observed frequencies to your expected frequencies, whatever that difference is, but comparing that difference to what you expected. And the analogy in the textbook is great. In summary, it's like this. So imagine you're having a party and you expect 1,000 people to show up, but instead 1,040 people show up. In that case, an extra 40 people is probably not that big of a deal. On the other hand, imagine you had a party and you expected 10 people to show up, but instead 50 people show up. In that case, an extra 40 people is actually a huge problem because you might not have enough food and drinks to serve 40 extra people in that context. So in other words, the way chi-squared test works is the difference between what you observed and what you expected, how big of a difference that is depends on what you expected. So everything is relative, in other words. All right, so let's go ahead and figure out what is going on here in terms of whether this difference is a statistically significant difference or not. So we're going to calculate the test statistic, chi-squared, and compare that to the critical value of chi-squared from your chi-square distribution. To read the chi-square distribution table, you need to know your alpha level, which we're going to use an alpha of 0.01, since that's the most common in social science research. And we also need our degrees of freedom. The formula for the goodness of fit test, the one we're doing now, is C minus 1, where C is the number of categories in your data set. So we have two categories, male and female. So therefore, degrees of freedom is 2 minus 1, which is 1. Okay, so with 1 degree of freedom and the proportion of 0.05, our critical value is 3.84. I'm going to write that down. Chi-squared critical is 3.84. All right, great. So the next step is to calculate your test statistic, and if it is larger than your critical value, you can reject the null hypothesis. So essentially, back to the formula for just a moment, we have to make all of those comparisons that I was referring to earlier for each cell in your table or each category, and then add them together with this summation symbol. So watch as we go forward here. Let's first start with the group on the left, the males. So chi-squared is equal to, we take our observed value of 143 and compare it to the expected value if the null hypothesis were true, which in this problem is 160. We square that difference, and the reason we square that difference is to get rid of the negative sign. We only care about distance in the positive sense because larger values tell us that there's a larger discrepancy between what we observed and what we expected based on H0, the null hypothesis. All right, and then finally divide by the expected frequency once again because everything is relative based on what you expected in this particular context. So then we do that for the females as well. The observed value of 177, subtract the expected value of 160, square that difference, and then divide by the expected value again. Okay. So let me go ahead and do those calculations. Looks like for the first grouping here, it's a 1.81. And then for the second grouping, another 1.81. And that gives us a chi-squared value of 3.62. All right, now 3.62 is not larger than our critical value of 3.84, which means our conclusion is fail to reject age 0. So in this context, what that means is that according to this sample of 320 people, there is not more female doctors under age 30 compared to male doctors. So we basically have to assume that the difference we're seeing here between 143 and 177 is just sampling error. It's not a large enough difference for us to conclude that among the population, there's more females than males. All right. So even though we did not find a statistically significant difference, let's go ahead and calculate effect size just for practice, which is phi. And phi is a measure of how big the difference is. And here's your size interpretations. So our chi-squared calculated value was 3.62. There were 320 people in our study. And that gives us a phi value of 0.11. And the small interpretation value is 0.1, which that is very close to, so you can call that a small effect. But it wasn't even statistically significant, so you could probably argue that you didn't even need to calculate this, but for practice, why not go ahead and do that? Okay, so this first example problem was the chi-squared test for goodness of fit. And there are two types of chi-squared tests discussed in this course. The second one is called the chi-squared test for independence. And we're going to use this problem right here. It says, for the using the chi-squared test for independence, use the following data to check for a relationship between the two variables, gender and pass rate. So imagine there's some course with a bunch of males and females in it, and we want to know if the likelihood of passing the course is related to gender, or simply put, if gender and pass rate are independent of one another, which is where the name of this test comes from, the chi-squared test for independence. Now again, what we need to do is compare our observed values, which are right here. These are the values that the researcher observed. We need to compare that to expected values in order to calculate our test statistic. However, the thing to consider here is that we actually need to calculate our expected frequencies using this formula right here. And that's because we have two variables to consider. And essentially, the expected values are based off of the null hypothesis, but we have a matrix to deal with, which adds sort of an extra level of complexity in determining these values. So before we go ahead and do that, let's actually look at the null and alternative hypotheses. And so the null hypothesis is essentially stating that the variables are independent of one another. There's no relationship. Whereas on the other hand, the alternative is saying there is a relationship between our two variables. That, in other words, the likelihood of passing the class is related to gender. All right, so in order for us to calculate the expected frequencies, we need to calculate some preliminary information first. I'm going to use a different color here to help me do so. The first thing I want to do is calculate how many people there were total in this pass column. So 16 plus 18 gives me 34 people in this column. And then I'm going to go ahead and calculate how many people were in the fail column. So 9 plus 12 is 21. And you can also use that information to determine how many people were in your study total, which 34 plus 21 tells me that there's a sample size of 55. But we're not done with our preliminary information yet. I also want to sum together the amount of people in each row. So for the male row, 16 plus 9 is 25. I'm just going to put that right next to that column. And then there were 18 plus 12, 30, 30 females in the study. And again, you can check your math. The males plus the females also gives you 55. So it looks like we did add things up together. All right, and so now essentially what we're going to be doing with this formula right here is calculating what would the expected frequencies be if the null hypothesis were a perfect predictor of these frequencies. So let's go ahead and create a new table to sort of mirror what we have in the table above. So we had the pass and fail columns, and then the male and female rows. Whoops, it's not the straightest line I've ever drawn, but that's okay. All right, now for each of these cells, we're going to apply this formula. So let's look at the top left cell. This cell right here corresponds to the top left cell up here. So this is the males who passed the class, the males who passed the class. And essentially, to calculate the expected frequency for that cell, I'm going to take the frequencies in that column. So this cell has 34 people in that column total. I'm talking about this box, and it's in this column. There's 34 people in that column total. And then there are 25 people in that row. So that's the FR. Frequencies in the row, FC is frequencies in the column. So 25 in that row, divided by n, which is the number of people in your entire study. All right, so 34 times 25 divided by 55 gives me a value of 15.45. I'm going to plug that in right here. So 15.45 would be the frequency you would expect for males who passed the class, assuming the null hypothesis is not true, meaning there's no relationship between gender and pass rate. This is the frequency you would expect in that cell, the males who passed the class, 15.45. All right, so it gets a little time consuming, but we need to do that for each one of these. So you can fast forward the video, or you can hang out with me as I do that now. All right, so I'm going to do the top right cell, the female. This would be the males who failed the class. Males who failed the class is the top right box in the matrix. Males who failed. So going down, my FE for that one, there are 21 people in that column and 25 people in that row. So 21 times 25 divided by the number of people in your study is 55. So 21 times 25 divided by 55, 9.45. And let's go ahead and put that here as well. 2 down, 2 to go. Let's do the bottom left cell. The expected frequency in that bottom left cell. So this box refers to this column of 34 in the total for that column, and 30 total in that row. Divide by 55. $18.55. Last but not least, the bottom right cell. The expected frequency is 21 times 30. So 21 is the amount of people in the column that box is in. 30 is the amount of people in that row. and then divide by 55, the number of people in your study. 11.45. Okay. So we did not have to do that step. We did not have to use this formula for question number 1 at the beginning of the video. You only have to do this for the independence test, because for the independence test, you're going to have 2 variables. And so finding your expected frequencies, if the null hypothesis were true, becomes a little more time consuming, but it wasn't too bad, just a few minutes. But now it gets back to the regular process, which is the chi-squared formula. And again, in the chi-squared formula, the basic process or the basic foundation here is you're comparing your observed values, the ones that the researcher actually collected, you're comparing those to the expected values if the null hypothesis were true. And if there's a large discrepancy between them, that is going to give you evidence that there is a relationship between your 2 variables, in this case, gender and pass rate. So let's go ahead and calculate our chi-squared value. So this process right here has to be done for every cell in your matrix or every box in your table. So we have 4 boxes. We're going to do this for all 4. So let's start with the top left box. The observed value was 16. Subtract the expected value of 15.45. Square that difference. And then divide by your expected value. And we do that for all 4 boxes. So add that to all of that information for your second box, top right. The observed value of 9, compare that to the expected value of 9.45, square that difference, divide by your expected value of 9.45, add that to your, let's do the third one, which is the bottom left, your observed value of 18, minus the expected value of 18.55, square that difference, divide by your expected value of 18.55, and then finally, bottom right box, the observed value of 12, subtract the expected value of 11.45, square the difference, and then divide by your expected value again. Okay, so we have some math to do. Let's go ahead and figure out what all this adds up to. It's always a good idea to check my work. When I make mistakes in these videos, those mistakes are going to carry forward, unfortunately. So if your math looks different than mine, double check yours and then double check mine just in case. So we're getting some pretty small values here, which means we may not end up rejecting the null hypothesis, which is fine. It is what it is. I'm seeing a trend as well. We got another 0.02. I'm always rounding to the second decimal point for consistency's sake. I guess the rounding brought this one to 0.03. So all of those together add to a test statistic of 0.09. Okay, now obviously that's extremely small, but where's the cutoff? Just like in the last problem, you need to identify your critical value for your test statistic, the critical value of chi-squared. With the independence test, your degrees of freedom is slightly different because we have 2 variables to consider. So C minus 1, the columns minus 1, so 2 columns, pass and fail, and then rows minus 1. There's the males and females, so there's 2 rows. 2 minus 1 times 2 minus 1. The degrees of freedom is 1. And let's assume, as always, we're using alpha of 0.05. Unless otherwise stated, we're pretty much always using alpha of 0.05. So let's go ahead and find the critical value of chi-squared. 0.05, 1 degree of freedom, happens to be the same as the last problem, 3.84. The critical value. So 0.09 is obviously not larger than 3.84. And so fail to reject H0. In other words, we have to assume that these two variables are independent. There's no relationship between gender and pass rate based on this sample data. And then just for practice, since we're here together, let's go ahead and calculate the effect size, phi, and interpret it. And I'm getting 0.04, which you might call that very small, which makes sense considering we found an insignificant relationship to begin with. Okay, so what we can now say is that according to the data, this chi-squared test suggests that gender and pass rate are independent of one another. There is no relationship between these two variables. Our test statistic was chi-squared equals 0.09. We had 1 degree of freedom in the study, and the effect size of phi was 0.04, which is considered a very small effect. All right, so there you go. 2 different problems for chi-squared. One was the goodness of fit test. The second was the independence test. Finally, as always, I want to encourage you, do a bunch more problems from the textbook as well as the study guide. The textbook has problems that go step by step that are going to help you kind of discern what's going on in these multifaceted problems. And of course, as always, please feel free to ask me questions if you have any.